Hello everybody, Adam Lusick here, and today we're going to be talking about how large language models are starting to be able to process multiple modalities, specifically images, videos, and audio. LLMs were originally created to primarily process text, being able to take some sort of text input and based on that input do some form of reasoning and generation of text output. But now these days, you can even pass in things like pictures or videos or audio files and have the language model actually be able to understand the contents of those non-text contents. And the ability to do this has proven quite useful, as if you think about language models as trying to emulate human behavior and human reasoning or thought, you would understand that we don't just see and process and understand things as text. We have all sorts of different senses that we use when actually interacting and understanding some sort of concept. And while this is happening in a more digital context, a large portion of how we as humans actually interact with computer-based systems is visual, through things like videos and images, and then also a decent chunk is going to be audio as well. So what we've been seeing is a very natural progression of making LLMs a lot more useful by leveraging their already robust understanding of human language behavior and reasoning through text, but bridging that over to auditory and visual information processing as well. And with some flagship models like Google's Gemini models starting to be able to do really crazy things like take in thousands of images per prompt or multiple hours of audio or a full hour of processing video length and still be able to do that text-based output based on the content there, I wanted to dig in a little deeper into how this is actually done. So in this video, I hope to break down all three of the non-text modalities that we've been seeing. That's images, videos, and audio understanding, and how a little bit of that research has actually historically played out to be able to give these language models these advanced cognitive abilities. And on top of that, a lot of this is going to be based on open source research, so I'll show a few examples of open source models that are able to do all of these different understanding tasks. As a quick note, the field of actually understanding all of these modalities digitally in some sort of deep learning setting isn't anything new, but I'm going to focus more on the modern language model and its integration with that text-based generation and understanding and processing of those. Starting, of course, by introducing vision with image understanding in language models. And this was really the first modality that started to get introduced to the LLM at a large scale with things like GPT-4. As I just mentioned, computer vision techniques have been around much longer than the large language model and all of these techniques, so we already kind of had, as a computer science society, an abundance of visual data and kind of some interesting approaches to understanding images in a digital setting first. So by the time that LLM started to emerge on the scene, the whole realm of computer vision techniques was already a pretty robust field. Things like AlexNet, convolutional neural networks, and whatnot had already started to be applied to different tasks like image classification, object detection, and even some sort of generative imaging and the starts of being able to actually use generative models to create novel images. And so I believe that this made kind of a natural starting point for being able to apply these to these text-based systems. On top of that, much of how we kind of operate as humans is through visual cues and signals. Obviously, our eyes are an important part of how we interact with the world around us, and so enabling language models and the kind of thought machine behind them to be able to see seemed like a very easy starting point, and that's exactly what we saw. Bypassing a lot of the historical methods for doing different computer vision techniques, we can look at one of the first examples of actually applying similar language model architecture towards vision understanding with the implementation of the vision transformer. So the vision transformer, if we zoom in on this picture a little bit, takes a picture and splits it up into 16 by 16 pixel patches. These individual patches are then going to be flattened into a sequence and projected into an embedding space along with a positional encoding. In other words, all of these 16 by 16 pixel parts of the image are going to be turned into numbers. Usually this represents the height and the width of the image as well as the color channels. And so all of that information about the pixels and their positions in the 16 by 16 grid, along with the color of them is going to be then split into all of these patches. And we're also going to append the positional embedding, which in this case is going to show kind of where in the actual picture, once it's been flattened into this sequence, it originally comes from. All of this information is then fed into the transformer encoder, similar to how text had been with words in a sentence, along with those aforementioned positional encodings. And through the transformer's self-attention mechanism, the model actually learns, through its training, the different relationships between these patches across the entire image. Very similar to how it determines the relationships of words across a full sentence. This allows us to capture global context and detail different spatial relationships of how things are actually situated in our image. What was found then is that the vision transformer can actually successfully attend to any region of the image from any other. So what that means is that it can learn these long-range dependencies of content within the image. The quick example that I wrote down here is relating one object in one corner to a detail in another, but the core of it is that this really proved that a pure transformer architecture can actually tackle vision tasks. This is, of course, great news as we work towards being able to understand and generate text from images, because it's a very similar architecture to how language models process text. But this is still more tackling the idea of actual vision encoding. Very similar to how BERT models do sentence encoding or language encoding, this isn't actually aligning images with text. However, that is where CLIP, or the Contrastive Language Image Pre-training model from OpenAI, actually starts to come into play. And so the CLIP model levels up from the vision transformer because it not only is able to encode images, but also text, all within the same model. And so essentially it is tackling the alignment of images with text. So the CLIP model was trained on a staggering 400 million image and caption pairs together. And what it was meant to do is take in a whole batch of these images and captions and predict which image actually goes with what caption and vice versa. And so through the deep learning process, it will make the encodings of the correct text and image pairs move closer together in its text encoding and image encoding embedding space, while pushing apart those that are not positive matches. Which more specifically, this technique is called contrastive learning, as it is, well, contrasting the images with the text captions and trying to make these predictions. More technically, this is effectively training a joint image text encoder to produce a shared embedding space for both of these modalities. And the outcome of actually training a system like this is that CLIP can then represent and understand visual concepts in natural language terms. This allows the model to do something called zero-shot classification, where after training, you can give a CLIP model a new image and a new set of text labels that are outside of the training set, and it will be able to then identify what label is closest to what image through its joint embeddings. This is done without any task-specific fine-tuning, which is the real neat part here. Essentially, this means that the CLIP model can recognize a wide array of image contents through just the pure scaled training on real-world captions here, which is essentially then bridging vision and language with zero-shot image understanding. So now we have a model that can understand images, understand text, and be able to do this comparison together with pretty much anything that you give to it that doesn't need you to do any sort of additional training. The next step, of course, is not just understanding this, but actually using it to be able to generate and make some meaningful insights. Which brings us, of course, to the first few models that were able to do this relatively successfully, coming from the Google DeepMind team, the Flamingo family of models. So what the Flamingo models do is actually integrate a pre-trained vision encoder along with a pre-trained language model and connect them together using a special technique called cross-attention. What this allows the model to do is generate text conditioned to the language model on the contents of images. without needing to retrain entire language models from scratch to do this task. The way that they do this is really interesting because they're able to actually take these pre-trained components like a vision encoder, something like a clip model or a vision transformer, as well as a language model, just an existing language model, and keep them mostly intact and the same. The only additions are this perceiver resampler as well as gated cross-attention layers within the language model itself. And these are going to act pretty much as the translation between the vision encoding into a format that the language model can actually understand, and are going to be components that are trained. The purpose of these two is first to resample what comes from the vision encoding. The reason that this resampling happens is because images can be input in any sort of format, length, width, height, color, all sorts into some sort of conversation that you're having. But you want to be able to support anything that comes in. That's where the resampler essentially is going to standardize the input from the vision encoder into a set number of features to pass through to the language model. The language model then has these gated cross-attention blocks that are inserted within the different layers of the language model itself at every so often specific layer. What these do is it takes the input from the resampled encoding of the images and converts that then more into the format and embedding space that the language model expects, along with the application of attention, so that the language model can attend to and understand and process through the data that's coming from our images. The gated part of this is more so controlling how much of the actual visual information is being passed through and processed at these specific points. And so the big benefit of being able to use existing and frozen vision encoders as well as an existing and unchanged language model, only just inserting these couple components in and then training those to be able to operate well in the full system as a connection, is that you can avoid kind of overfitting or drastic forgetting of the language model's actual capabilities. So you can pretty much keep everything that the language model has learned and add on top of it the ability to see and process images. As a bonus, this inherits all of the same benefits of a language model, essentially being able to do things like few-shot learning or just providing a few examples of a task you want to do, now with visual components, and then relying on the language model's underlying system to be able to do that. Their example was generate relevant captions or answer kind of questions about images, given just a few examples there. So at its core, they were really able to demonstrate kind of an improvement from passive image understanding to actual active generation of text and answers based on image information. And this is where we're really going to start seeing this idea of taking pre-trained existing components, things like vision encoders, clip models, vision transformers, all the likes, as well as pre-trained language models, and figuring out some sort of efficient or effective way to do some training to encourage the actual understanding of different modalities. And this idea of creating kind of an efficient adapter to do these tasks didn't really ever go away. So one of the next things that came about for understanding vision was the introduction of the TimeSFormer in the Blip2 paper, or bootstrapping language image pre-training with frozen image encoders in large language models. This takes the idea of what we saw with Flamingo almost to the extreme. By training a lightweight kind of transformer network here with a purely frozen image encoder and purely frozen large language model to be able to actually bridge both in between. Blip2's training follows a two-stage process. The first is that vision language representation learning, similar to the kind of encoding that we saw with vision transformers and with clip models, where in this stage, the TimeSFormer is trained to interpret and extract all of the useful information from the frozen image encoder. The theory behind this is that the TimeSFormer kind of queries the image features as it has these learnable query tokens that attend to the image encoder's output. And then it's trained using paired images and text to produce embeddings that align with textual meaning. So it's going to try and take the encoding from our frozen pre-trained image encoder and essentially produce a new encoding that is a compacted representation of the image that mostly tries to capture just the relevant information. So once we're able to extract the text relevant encoding through the Q-former from the image encoder, what we need to do then is connect it to the language model and be able to train it in a way that it converts the encoding into something that the language model can actually understand. So in the second stage, that's where we do the vision to language generation learning, where in this, what we do is we connect the Q-former to a frozen language model, and the goal now is to try and generate text with the Q-former's image-informed embeddings. So the output from the Q-former is fed into the language model, and through training and tweaking, of course, the Q-former in this training, it tries to generate the appropriate kind of text, whether that's captions, answers, etc., for some sort of given image. So during this stage, the LLM is not updated, and we only tune the Q-former. The result is this transformer model that can connect the image encoder to a language model in a format that understands the most text-relevant parts of the image encoding and outputs in a format that a language model can actually understand and use in its predictions of text. And the cool part about this is that it actually performed very well, outperforming the 80 billion parameter Flamingo model on zero-shot image question and answering, with 54 times fewer trainable parameters, with the added benefit that you can actually swap in and out different image encoders and language models as needed, just needing to train a new Q-former to connect them together. Moving on to modern-day vision language models, we've tended to standardize on kind of this similar modular architecture, using a pre-trained image encoder, some sort of multimodal projector module, which is able to take in that image encoding and convert it into something that our text decoder, which is going to be generating the text, can actually understand, and putting them together. The image encoder is often a vision transformer or some sort of clip model. It produces the representation of the image, and then the projector maps that into the language model's embedding space. This is a great approach because it's super efficient. Much of the heavy lifting is done by different components that were already pre-trained on vast amounts of unimodal data, so images or text, and then only a small part of that is needed to bridge them together to leverage both the advanced understanding of both modalities. For a quick example, I'm going to highlight the lovely small language model Moondream. This is a almost 2 billion parameters, just under, small language model based on the Phi architecture from Microsoft that's been trained very well by Vic Korapati and his team to do all sorts of different vision language model understanding tasks. If you're working in a GPU accelerated environment, you can see the code for using the Transformers package, Hugging Face's package for running Transformers-based architectures, to actually ask about a picture. So I ran it through something like this, which is just a cat holding up a sign of my name, and said, can you describe what's going on in this image? And it's able to accurately say that the image features a ginger cat with a white chest and paws, standing upright holding a piece of paper. The paper the cat is holding has the name Adam Lusek written on it, as well as some more specific features like its eye color even. If you're not working in an environment with a more beefy computer, you can also hop over to Hugging Face and check it out in the spaces. So I'll ask it to describe this image of this cool looking website. So puts together a very nice description here of what it's seeing. But with that, we can move past static image understanding to some of our other modalities, specifically, of course, videos and audio. And the reason I spent a lot of time discussing the different techniques from vision is because many of them are actually applied back to do the others with video and audio. Video is an interesting one because if you think about moving from image understanding to video understanding, the first thing that you'll realize is that videos can be thought of as pretty much just a sequence of images. So we can leverage a lot of the image understanding that we have already, but with one key difference. Notice that I said a sequence of images. So there is that new dimension here of time. While images are static and just a snapshot of the kind of information that you're processing, videos capture a whole lot more. Of course, there's that temporal dimension that captures things like motion, timing, and different relationships that happen across a whole scene or across a whole video. So we must account for this as we go from processing just single images to multiple in a row in what we know colloquially as a video. As a fun plus, this is also where we start to talk about spatial understanding as well, because this represents kind of how things are positioned across time. So this is where the very sci-fi sounding space-time model comes into play, which doesn't necessarily talk about, very cool things like spaceships or whatnot, more how things change or how things are processed over time and how they kind of move or are positioned. So to kick us off here, very similar to what we saw with images, is the introduction of video transformers. Building on top of the existing vision transformers, things like TimeSFormer adapt it for videos by enabling attention within each frame and across frames. So it uses what they call a divided space-time attention mechanism, where with each one of these transformer blocks, it applies self-attention over the temporal dimensions separate from the spatial dimensions. This is a very fancy way of saying that it just separates its understanding of when something happens and also where something happens into two separate calculations, not trying to do this jointly at the same time. So this takes the original patches of something like a vision transformer and views these more as a sequence of these patches to introduce the temporal and spatial components. Another further example of what we mean by divided space-time attention is that the TimeSFormer model first attends to the tokens, which it extracts out of the image frames, along the time axis, which captures how a particular patch or location evolves over the frames, and then attends to the tokens within each frame, which is where you get those spatial relationships that we were already starting to see in the original vision transformer. But at the end of the day, similar to what we saw with the vision transformer implementation, we proved once again that a pure transformer can effectively learn video representations, or take in a video and encode it into something meaningful using and extending on the different image transformer approaches and techniques. One of the techniques that was found to be very useful for vision encoding and pre-training was the idea of masked predictions, along with the already aforementioned contrastive learning that we saw in something like the clip model. The model VideoMAE applies this in a few specific ways. It processes videos as a sequence of tokens, or the patches across frames, and masks a large portion of them during training, or essentially just takes out and replaces with blanks portions of these patches of the videos. Its training is then encouraged to reconstruct the missing packages here, and through reconstructing and comparing to the original perfect video that's unmasked, it learns very meaningful spatiotemporal features from the context that it's passed through. And with a few specific techniques along the way, the VideoMAE model really encouraged the encoder to extract very rich video representations from this training method. But this method of encoding videos into the rich semantic numbers needed for something like a language model to do text generation from was not the only thing applied. We still, of course, use the contrastive learning, which brings us to something like Intern Video 2. Intern Video 2 is what's called a video foundation model, which is essentially a very powerful model that's able to take in videos and encode them into rich representations. These representations, of course, are going to be in numerical format. The training of Intern Video 2 follows some very interesting techniques, cleverly combining a lot of the things that we've went over. The first stage is the masked video modeling, so similar to what we saw with the VideoMAE just now, is that the video encoder is initially trained using this masked video token reconstruction task. This is where it starts to do that prediction and use self-supervision to create the low and mid-level video understanding. This is then bolstered through some cross-modal contrastive learning. So very similar to how the contrastive language image pre-training model, or the clip model, was created Intern Video 2 aligns these video representations with text and also audio, but we'll get into audio a little bit later. And what it does is it takes the video encoder, which is first trained in stage 1, and uses the contrastive learning with video and text pairs to align its encoding with text. So at this stage, it has a relatively robust understanding of videos and is able to match that understanding with text itself. This allows us to do something like attach it through with a Q-former to a pre-trained language model, which is exactly what the researchers behind Intern Video 2 proved to be effective. So using their now very well-versed video encoder, what they do is use pretty much the same exact training technique as we saw in the Blip 2 paper to train a Q-former to align that representation with some sort of frozen pre-trained language model, which at the end, as was possible with images, allows us now to pass in videos for understanding to the language model to do some form of video generation, processing, and reasoning output. Moving on to modern day video understanding in large multimodal models, some research out of Meta with the release of their Apollo video understanding model family shows us a little bit more of the behind the scenes of what modern day video understanding looks like. They were able to achieve the best results in video understanding with large language models through combining two specific encoders. One is the SIGLIP encoder, which stands for sigmoid loss for language image pre-training, which better captures spatial details of frames, along with the Intern Video 2 encoder, which better captures the temporal dynamics. Combining these together, they were able to then achieve very robust spatiotemporal understanding, superior to just using one or the other individually. They also bring back one of the favorites, the perceiver resampler, which, if you remember, we saw in the above Flamingo models here to better represent then our encoded models back into the language model. The benefit of this is that it condenses the frame level features into compact sets of tokens that only keep what it thinks is the most relevant parts of the visual elements of the video that are needed for actual text generation. A few other fun techniques that they prove to be effective is that sampling videos based on a frame per second strategy, selecting different continuous frame snippets rather than uniformly cutting up videos, maintained that kind of natural temporal order across larger videos for more robust understanding. But you can see now how a lot of the foundations of actually connecting vision understanding to language models have been used and improved upon to do something like video understanding as a second phase. As our example, we can use something like Qwen 2.5 Vision Language 3 billion Instruct, a little bit of a mouthful language model. That is a 3.75 billion parameter, small by today's standard language model, built for different multimodal understanding. I have this Creative Commons quick video clip here that I'll play. Not the highest of quality, but it is a nice looking bakery here with some bikers and people walking past. So let's see if those minute little details are able to be picked up by the vision language model. The code for this is going to be a little bit more involved than our Moondream example. Much of it was just taken directly from their Hugging Face model card here, but we're going to be loading the model as well as a processor for this specific Qwen model. We are then going to pass in, of course, our MP4 file, and we're going to downsize it a little bit into 360 by 420 pixels. It should not degrade the performance too much. We can see, however, that they did take some of the findings that we were just talking about with sampling into account, and you can do different frame per second sampling. So I'm just going to sample 1 frame per second here. Passing that all into a chat template and then passing in the image and video inputs all through its processor here, we can ask it to describe what happens in this video. Where we get out, the video starts with a view of a street scene featuring a bakery named, not going to try it right now. The bakery has a blue storefront with large windows displaying various baked goods and pastries. People are walking by on the sidewalk, and a cyclist rides past. The camera then pans to the right, showing more of the street and the adjacent buildings. The video ends with a clear view of the bakery's exterior, which, as we saw in our quick walkthrough, it wasn't the most exciting of videos, but we can see that it was able to process and understand it pretty well. So with video and image understanding out of the way, the last thing that we need to touch on then is past vision to a different sense of ours, hearing, or audio understanding in large language models. While different vision-related tasks might be more immediately useful, audio is still a key frontier for understanding and processing. Audio understanding, whether it's something like speech or just general acoustic sound, allows AI models or language models the ability to grasp information conveyed in things like spoken language, environmental sounds, and others like music. Incorporating this allows us to add in interesting context like tone of voice, background noise, nonverbal cues, and other things that pure text or vision-enabled models might miss. So really enabling language models with audio comprehension is slightly overlooked in the field, but super important for real-world applications, complementing the visual and textual understanding of language models. But similar to what we've seen in the past two examples, much of the actual learnings from vision and video understanding can also be applied to audio, because audio also has somewhat of a temporal aspect to it, in that it is usually some form of information displayed over time, and it can even have a visual aspect to it, like a spectrogram or a waveform. While not the main focus of this presentation that I'm running through, much of the early work in understanding with deep learning techniques was focused around speech. Models like Wave to Vec set some early foundations for converting raw waveforms into meaningful representations. It uses some of the techniques that we saw before, things like masking portions of waveforms encodings and having it predict what should be in those masked spots, as well as having contrastive objectives similar to things like the clip models. This was all used, of course, to be able to encode audio into a rich embedding that preserves all of the audio-specific nuances like tone or speaker identity. And of course, when talking about deep learning and audio understanding or speech understanding, you have to mention the advancements that OpenAI's Whisper model showed. Well, this does jump ahead a bit in our linear story of how audio understanding is applied to language models. Their approach of applying the encoder-decoder transformer architecture onto automatic speech recognition is one that is still relevant to this day, with many people relying on the Whisper model for automatic transcription. But keeping in line to what we've seen with the prior modalities, it all can start with the audio spectrogram transformer. This is where you can probably see something very interesting, and that a lot of this looks very similar to the vision transformer in that it is taking 16 by 16 patches of an input spectrogram, which is essentially kind of a time series heat map of an audio file, and split it up into these patches. These patches are then projected into the transformer's embedding space along with positional encodings. This very literally takes the idea of audio and treats it almost like an image. Very similar to what we saw with our vision transformers, even leveraging pre-trained vision transformer weights to adapt a VIT into a model that can actually accept these spectrograms. So quite interestingly, we pretty much transferred image understanding over to audio understanding using almost exactly the same technique. And as a result of this, we once again prove, similar to the successes of our images and videos, that transformers are a capable architecture for processing, understanding, and encoding audio. In keeping with the similarities that we see with images and audio, a CLAP model, or contrastive language audio pre-training model, was also created. Very exactly similarly to the CLIP model, it's going to take pretty much the same kind of approach taking encodings of audio and encodings of text and aligning them together through this contrastive pre-training. So it's going to take the text audio pairs, try and predict which ones go with what, and move those closer together in its learned embedding space and move the others farther apart. And we saw exactly the same results, with the clap model being able to have the same zero-shot classification abilities on unseen text audio pairs. So now through this model, we can learn audio concepts through natural language supervision and align the two together in a shared embedding space. And to show really how similar audio understanding was to the advancements of image understanding, the next example is the audio Flamingo model, which takes all of these encoders and puts it together into a audio understanding language model using the same techniques that the original Flamingo models for image understanding used. Similar to what we've seen, some form of audio encoder, whether it's a clap model or a Wave2Vec style model, is going to do the encoding, and then all of those representations are going to be ran through the cross attention layers, which are intertwined between frozen language model blocks. This allows us to then take all of this text and audio input and be able to have the language model itself attend to what is most relevant during its reasoning and generation. And once again, this allows us to leverage all of the existing capabilities from the frozen encoder as well as the frozen language model, things like in-context learning with few-shot prompting, supporting multi-turn conversations and different understanding about what the language model now hears, and using a lot of the same techniques, as we mentioned, from vision training. And not to stop there, the powerful idea of the Q-former was also applied to audio with something like the GAMA model here, or Generalist Audio Model for All. Using similar techniques to what we saw with things like Intern Video 2 or the ClipFormer model, we're able to pass in all of the audio features and have a couple other things around it that help kind of aggregate all of the information that we're seeing from audio. But the main bulk of it is that we can also use the same kind of adapter architecture to connect the actual representations into a format that a frozen large language model can actually understand and able to do advanced reasoning through different audio inputs. Which brings us to our audio example, which we'll be using the model, another Qwen model, Qwen2 Audio 7B Instruct, an audio-specific tuned model that has the back and forth chatting capabilities, and we'll be passing in the sound effect of a car starting, which I shall play. Great sound effect. And so then after loading the processor and model from Hugging Face, what we can do is pass in the wave file here and ask it to describe this sound in detail. And then of course, after processing it, loading the audio file and having it all get processed into a format that the model can understand, we generate from it and get our response, which is the audio contains the sound of an engine starting up and revving, followed by the sound of it idling loudly. I wanted to use this example specifically because there are a lot of different models that can do sort of speech understanding, but I think it's always really cool when you have a model that can understand not just spoken speech, but different auditory signals like these. But now with all of these modalities kind of discussed and their evolution to actually connecting into language models, you're probably wondering, what now and what's next? Well, first, just to sum up a little bit, much of what we've seen has kind of unfolded consistently in a three-stepped pattern, starting with some sort of specialized encoder for each modality that actually encodes all of our different content into some sort of form that is more numbers, of course, and a rich embedding representation. And then that representation goes through some form of alignment where it is aligned with text embeddings, bringing it closer in embedding space to text representation so that we can start to attach it, of course, to a language model. So those aligned representations then integrate back into a large language model's understanding through some form of adapter, which enables multimodal generation, reasoning, conversation, and interactions. We can look at more complicated architectures like the more recent Llama 3 models and see that they're still using things like different encoders and adapters as well as cross attention to feed these back into their foundation models for this full multimodal understanding. And as I mentioned earlier in the video, a lot of foundation models are starting to natively integrate multimodal understanding and reasoning alongside their basic text offering. This, of course, unlocks a whole heap of different possibilities of things that you can do with these. Past text, things like image-guided Q&A, automated video summarization, semantic search and multimedia databases, audio transcription, sentiment analysis, context-aware robotics interactions, OCR, all sorts of things. Multimodal content generation, understanding. It's a very, very cool concept that brings language models one step closer to the cognitive abilities of humans, especially interacting in their worlds, which are the digital realm. I personally use these capabilities in a lot of different projects, both personal and private, and some of the ones that I've posted, which I won't go into depth as I've had some videos covering these, is things like PowerPoint to description, where I use vision language models to convert PowerPoint presentations into detailed textual descriptions, able to capture both text content as well as visual relationships across different slides, and things like Needle in a Vid Stack that automates video content extraction by processing audio tracks using Google's Gemini AI models, which enables me to do precise semantic searches across extensive video collections. So unlocking all of this multimodal understanding really allows you to do some super cool things. Hope it got some kind of ideas floating maybe in your head already. But past this, one of the last things that I want to talk about is not just understanding video, images, text, and audio, but also generating it all in one. I sincerely think that large multimodal models, or those that are able to do both the understanding and generation of content on the fly, are a very interesting topic to keep an eye out for different future models. And we're even starting to see some of the signs of this popping up, like in Google's Gemini 2.0 that has native image generation as well as text generation. What we can do is prompt it with something like an image and say, maybe can you make the green and orange gradient instead? And go ahead and try that out. And after a few seconds here, we should get that response back. There you go. And it will try its best to then generate an image here with its internal capabilities in just one model. And of course, we've seen things like ChatGPT's advanced voice mode, which is a direct voice-to-voice processing through their language models. What's up, ChatGPT? You're on video. What do you want to say to the viewers at home?
Hey everyone, thanks for tuning in. If you're enjoying this, don't forget to like and subscribe for more fun content. If you have any questions or suggestions, drop them in the comments below. Let's keep this conversation going.
That's a pretty base ChatGPT if I've ever heard one. But with those amusing examples out of the way, what we can really see is that being able to embrace not only the input modality, but also generate across various output channels, we can move towards AI systems that begin to even more closely mirror human cognitive flexibility, translating between different forms of perception and expression, removing the different barriers between these modalities and creating a more intuitive and natural human-machine interface. So all in all, hope you learned something interesting today about the different modality understanding and processing and connecting these through to large language models. As ChatGPT said, if you like the video, want to see more, subscribe, and if you have any questions or comments, leave them in the comments below. If you want to support the channel even more, consider dropping a super thanks donation or joining a membership. Thank you and have a great day.